Okay, so thanks for your reply. Then I assume everything is working. Okay, so for today, we are going to have the MSc seminar for this semester. And we are very happy to have Dr. Ivan Yim today. So he will present us, okay, on a topic of the lanthanide self-assembly supramolecule architect with sensing property. So Ivan has been graduated from the Hong Kong Polytechnic University, so with a PhD degree. And he just joined our department as a lecturer somehow in the early April. So without further ado, so let me pass the stage to Ivan.
Okay, thank you, Gray. Today's topic is lanthanide self-assembly supramolecular architects with sensing properties. Thanks for invitation by Dr. Gray, and I am Dr. Ivan Yim, and I'm an inorganic chemist, and my research mainly focused on lanthanide chemistry, coordination chemistry, and preparation of asymmetric supramolecular assemblies. Okay, so here is today's content for this seminar. At first, I will introduce to you about what lanthanide is and about supramolecular cell assembly complexes. And then I will talk about the mechanism and design of sensor. And then I will give some examples of lanthanide supramolecular complexes with sensing property. And finally, I would like to introduce to you all about the challenges in developing lanthanide supramolecular sensors. So here is today's topic, lanthanide self-assembly supramolecular architects with sensing properties. So this topic is a little bit confusing, so I would like to introduce the terms one by one. So I would like to start from self-assembly supramolecules. So what is meant by self-assembly? Self-assembly means the small components aggregate comes together to form a well-defined structure through some specific molecular recognition. And for supramolecules, it is formed by small component interact through non-covalent interaction. And this kind of non-covalent interaction is useful for developing highly complex chemical systems. So based on this slide, you can see the self-assembly supramolecules means the small component aggregate together to form a giant large supramolecules through hydrogen bonding, metal coordination, van der Waals forces, as well as some of the pi-pi interactions. So here shows one of the example of self-assembly supramolecule is the formation of micelle. So the micelle is formed by the phospholipid bilayer. So the phospholipid is composed of the hydrophobic head and your hydrophobic tails. So when you put this hydrophobic into the water, phospholipid into the water, and then the phospholipid will come and aggregate to form a phospholipid dispersed in a liquid. And this one we call it micelle. So you can see in the structure of the micelle, the hydrophobic head will point outside to join the water molecules. And for the hydrophobic tail, they will point toward inside. And in the micelle, the area inside the micelle will be a hydrophobic environment. So another example of cell-assembly supramolecule will be DNA, as well as the phospholipid bilayer in your cell membrane. Okay, so after talking about self-assembly supramolecule, and I would like to talk about what lanthanide is. So here shows some of the news that I captured on the internet. So you can see lanthanide metals, rare earth, and then rare earths. And then these terms always appears during the period of trade war between China and US. So what is lanthanide? So here shows the periodic table of lanthanide. So you can see the lanthanide is in between 6s orbital and 5d orbital. And then in between 6s and 5t, you can see a series of 15 elements. And this 15 element we call it lanthanide. So the valence shell electron of this lanthanide will be 4f orbital. So the period below lanthanide will be we call actinide. This period will be 5f orbital, but we are not going to discuss actinide here. So for lanthanide is different from rare earth, as we can see here. You can see rare earth and then lanthanide. Actually, lanthanide is a series of these 15 elements. So rare earth is these 15 lanthanide plus yttrium and also scandium, these two elements plus lanthanide, and then composing the term called rare earth. So what is the different, what makes it so different about lanthanide? So lanthanide is a very different coordination chemistry compared with some main group elements such as copper, nickel, okay? The lanthanide 4f orbital do not participate in bonding significantly. So the right-hand side shows the electron probability distribution of this different orbital. So you can see the outermost shell of lanthanide is 4f orbital, but it locates even closer than 5s and 5p orbital. So when ligand coordinate with lanthanide, and the ligand will be well shielded by the 5s and 5p orbital. That means the 4f orbital will not affect that much by the ligand. So you can see the crystal field effect are weak compared with transition metal, because I think most of you may learn about transition metal chemistry. So you learn about crystal field, you learn about ligand field. So you know when the transition metal coordinate with the ligand, and then the ligand field will spread into Eg, T2G, right? But for lanthanide, the orbital, the energy level will not affect that much by the ligand, because the 4f orbital is well shielded, well protected by 5s and 5p orbital. So the most stable oxidation state of lanthanide is +3, although you can still find some of them are +2, for example, europium, and also some of them maybe cerium is +4. So because of this charge +3, it makes lanthanide to become a hard Lewis acid and prefer to coordinate with hard base, for example, O and N. And lanthanide exhibit a very large coordination number from 3 to 12. So you can see, going back to the periodic table, you can see it's located on the 5th period. That means the atom of lanthanide is very large. So it can coordinate with a lot of ligand compared with transition metal. So it accommodates large coordination number from 3 to 12. And the most common by far is around 8 to 9. So the structure below shows some of the common lanthanide chelating units. So you can see some units are beta diketoning, pyridine 2,6 dicarboxylic acid, etc. More of them contain a hard base such as O and N. Okay, so and then I will introduce some of the lanthanide photophysical properties. So lanthanide exhibits a very unique photophysical property, because as I mentioned before, for the 4f orbital, the ligand perturbation are minimized because of well shielded from 5s and 5p orbital. Therefore, lanthanide exhibits a characteristic narrow-like emission spectrum. And the right-hand side shows a simplified Jablonski diagram of the emission of lanthanide ions. Okay, let me yes, yeah. So I mean the emission is here. The emission is from the excited state to the ground state, but such transition is FF transition and is forbidden in nature. So the direct excitation from the ground state of the lanthanide to the excited state is forbidden. Okay, it won't possible. So scientists discover a method we call it antenna effect. What does it mean? That means the ligand coordinate with the lanthanide ions, and then the energy will be first absorbed by the ligand, and then the electron is transferred from the ground state to the excited state, and then undergo the intersystem crossing to the triplet state of the ligand, and then the energy or the electron can be transferred to the excited state of the lanthanide, giving out the lanthanide emissive luminescence. And the figure showed below is some of the relative emission intensity of some of the lanthanide ion. And these lanthanide ion, most of them are +3. Okay, so this graph is showing the +3 lanthanide ion. So you can see some representative lanthanide emission. For example, EU3+ is red in color, and for the emission of TB3+ will be green. Okay. Okay. So you may ask about, okay, so lanthanide is so exhibit unique photophysical properties. So is there any modern application for this, right? Lanthanide is widely used for many applications, and one of them are the security ink in banknote. So this 5 shows the Europe, okay? So if you, okay, so if you excite the banknote at 254 nanometer, you will observe a blue-green emission on the banknote. And this emission actually is attributed to the presence of EU2+. This time people use 2+ complex to put it on the banknote for security ink. And the actual structure, actually, we don't know because it's security reason. But one university suggests that the green color may caused by this complex, this EU2+ complex. Okay, so we talk about lanthanide, we talk about self-assembly supramolecule. So how about if we combine them together, lanthanide self-assembly supramolecular complex? So what it is about, actually, when we are going to prepare lanthanide self-assembly supramolecule, actually we prepare a ligand and we prepare some of the lanthanide ions. And then the general procedure for preparing this compound is easy. We just need to add the lanthanide ion into the ligand and then reflux to give the most thermodynamically stable product. So you can see here, so one of the example. This one is the C2 symmetric ligand. So if we put this ligand and then put this metal in a round bottom flask and then reflux it, and then we can get the cell assembly stable product. So this one we will describe it as a cage, or we describe it as a tetrahedron. So for the preparation of tetrahedron, we can use either edge-directed ligand or we can use face-directed ligand to prepare this kind of supramolecular compound with an inner cavity. So as I said before, the preparation of this compound is very easy. You just need to mix the ligand and then metal and then put it in a flask and then reflux. You can get the supramolecular compound. So in laboratory, when you are going to prepare this kind of supramolecular compound, you are going to mix the metal to ligand in a ratio of 2 to 3. Why? Because in the desired supramolecular compound, we got 4 metals and we got 6 edge-directed ligand. So theoretically, if we mix the ligand and metal in a ratio of 2 to 3, we can get this structure. However, there are many possible products that can be formed by this ratio. We may get M2L3 helix, we may get M6L9 triangular prism, or we may get M8L12 cube. So they are all having the same metal to ligand ratio 2 to 3. And that's why that's the difficulty when we are going to prepare self-assembly supramolecule, because there are many possible products that is difficult to control the result. So this slide shows a general, very brief visualization of cage sensing. Okay, so this slide show a turn-on sensor. For example, if we have a luminescent inactive cage, and then through the interaction between the substrate or the analyte with the cage, and then the substrate or analyte will be encapsulated by the luminescent inactive cage. And then upon stabilization, the cage may induce luminescence, which can tell people that the presence of this analyte. But this is only one of the example of sensor. Actually, there are many different mechanisms. For example, the substrate may interact with the metal center or interact with the ligand rather than encapsulated by the cage. So I'm going to introduce 3 different types of sensor, okay, which are turn-off sensor, turn-on sensor, and also ratiometric sensor. The first one we call it turn-off sensor. That means the fluorescent intensity is quenched. So initially, the complex is emissive, and upon the coordination or the interaction with the analyte and the receptor, and then the fluorescent intensity is quenched, and this one we call turn-off sensor. So for turn-on sensor, it's vice versa. Initially, the complex is not emissive, but upon the interaction between the analyte with the receptor, and then the fluorescent intensity enhanced, and this one we call it turn-on sensor. So in general, turn-on sensor are highly preferred over turn-off sensor because the bright signal is easier to detect in a dark environment. And if you are working on some of the cellular imaging, then I think turn-on sensor will be more sensitive because the background emission of cellular imaging is very high. So using turn-off sensor may not be that sensitive. So the third one, we call it ratiometric sensor. Actually, it means the sensor with a distinct change in fluorescent intensity. So in this kind of ratiometric sensor, it may incorporate 2 different fluorophores. So upon the interaction between the analyte with the receptor, and then the intensity of 2 or more fluorescent emission band will change. And the right-hand side shows one of the example. This one is a fluoride ion sensor. So you can see those scientists monitor 2 different wavelengths. So when they add more and more fluoride ion into the complex, and then the emission intensity at 490 nanometer drops significantly, while at the same time the emission wavelength at 582 increase steadily. So this kind of ratiometric sensor can increase the accuracy and also reliability of the quantitative analysis. Because if another case, the emission wavelength at 490 drop, while at the same time, the emission intensity didn't change at 582. That means there is some interference. The signal decreased not because of the presence of fluoride ion. Then that means the ratiometric sensor can increase the accuracy. Okay, after introducing the general type of sensor, then I would like to give a very brief introduction about the mechanism of the sensor. So you may ask why some of the sensor can be turned on or turned off. Actually, this turn on or turn off mechanism can be explained by 2 different mechanisms generally, which are PET and another one we call it FRET. So for PET, PET stands for photo-induced electron transfer. So PET is a electron donor, electron acceptor interactions. So for example, on the right-hand side shows one of the example is turn-on sensor. So what does it mean? Remember the sensitization of lanthanide ion required the antenna effect. So for example here, the fluorophore was first excited, and then the electron will be promoted to the lumo. So imagine if you have a receptor, that is electron donor. And then once the electron is promoted to the LUMO, and then the electron in the electron donor will donate the electron to this HOMO. And then the fluorescence will be quenched because this electron orbital is fully occupied. So however, if we have a analyte, for example, the analyte coordinate or interact with this free acceptor, which lower the energy level of this HOMO. And then the band receptor with a lower energy HOMO. And then that means this pair of electrons cannot donate to this HOMO anymore. And then so the electron on this LUMO can be released and released as emission. Okay, so this is the general concept of turn on center by PET. So how about turn off sensor? I think the mechanism is similar. So for example, here, the electron can be first promoted to the LUMO and then released to the HOMO. If there is a band receptor that has a HOMO near the LUMO of the excited fluorophore, and this receptor is a electron deficient compound, then the energy here, the electron on the LUMO can donate the electron to the HOMO, which also quench the overall fluorescence. So as you can see, the PET focus on the MO between the fluorophore and the receptor. So the energy gap between different MO is the driving force for the PET. And PET plays a major role in the fluorescent quenching process. So one of the famous examples is the turn-on cation sensing using this mechanism. So another mechanism, we call it FRET. FRET stands for first resonant energy transfer. It is a long-range bipolar interaction. So on the right-hand side shows the mechanism of this FRET. So the energy can be first promoted to the LUMO, and then upon the relaxation of this electron back to HOMO, and then the energy will be transferred simultaneously to the acceptor. And then the acceptor energy from the HOMO can be promoted to the LUMO. So this one is different from PET because PET concerned about the electron transfer, but for FRET, it concerned about the energy transfer. And that's why the distance become longer compared with PET. So for FRET, it can transfer the energy up to 100 Armstrong. And this FRET strongly depends on the overlap of the fluorescent emission spectrum of the donor and the absorption spectrum of the acceptor, and also the distance between the donor and acceptor. So these two points are important because when people are preparing chemosensor, they have to know which energy transfer mechanism. So one of the very useful criteria is they have to monitor or they have to investigate the fluorescent emission spectrum and absorption spectrum. If there is no overlap between these two spectrums, then they can conclude that the energy transfer is not done by FRET. Okay, so here's some of the general energy transfer mechanism. And then I would like to talk about the design of chemosensor. So after knowing about what is lanthanide, what is supramolecular complex, and as well as some of the mechanism, then when you are going to prepare a chemosensor, you have to think of different criteria. So I divided these two criteria in supramolecular complexes and also target analyte. So these two criteria is closely related. For example, if you are going to prepare a complex, so you have to think of the ligand design. For example, the size of your supramolecular complex, the topology, where you want a cage or you want a cube or you want a helix, and then the signaling unit. And then you have to think of the photo-induced process, whether you want PET, you want FRET, or you want inter-ligand charge transfer. And also you have to think of the expected photophysical property of your complex. For example, which lanthanide you're going to use. You want green emission, then you use TB, or you want red emission, and then you use EU. And also you need to think of whether you want to make a ratiometric sensor. That means if you want to use a ratiometric sensor, then probably you have to incorporate 2, 4, or 4. And on the other hand, if you're talking about the target analyte, so you have to think of which one will be your target. For example, what is the characteristic of this analyte? Is this a charged species? Or what is the size of this analyte? What is the recognition unit of this analyte? And also the sensing medium. Are you going to perform the sensing in water, in buffer, or in organic solvent? Then I think these 2 criteria you have to think before really performing the experiment of sensor. Okay, so concerning about the ligand design for supramolecular fluorescence sensor, actually, this is the key step, I think, because it's strongly governed the result of being a chemosensor. And the careful ligand design is a must for designing a cage, because sometimes you may form a helix or form some unwanted metal cluster. And you have to make sure that the complex that forms is able to encapsulate the target analyte. And some scientists also incorporate some of the functional group on the ligand for some of the potential applications, such as catalysis and sensing. And of course, this compound must be luminescent. So here shows one of the examples of the ligand design for supramolecular complex. So with the use of this tridentate C2 symmetry ligand, so you can see in between 2 metal chelating unit, we got a monophenol unit. And then upon the coordination of European 3+ ion, it forms a EU4L6 tetrahedral cage, which is this one. So the scientist wants to make an even larger cage. So what did he do? He tried to extend the central linker into a biphenyl unit. And what he wants is getting a larger cage. Unfortunately, the incorporation of lanthanide ion forms a EU2L3 helix. And that means even if you extending the linker with a very slight change, the supramolecular complex will give a very different result. Okay, and although the formation of lanthanide supramolecular complex is very challenging, but there are still some of the advantage for using this kind of method to make chemosensor. For example, as I said before, the preparation is very simple. You just need to mix the ligand and then mix the ion and then reflux it, and then you can get the most thermodynamically stable product. And most of the time, the ligand consists of about 3 to 4 organic synthesis, which is quite convenient. And another key advantages is the preparation of a wide variety of supramolecules. And this type of supramolecule actually governed by many different concentrations, different conditions. For example, if you change the concentration, if you change the cation, changing the anion, or even solvent, then it will give you a very different supramolecular product. That means you can prepare a wide variety of supramolecules by using the same ligand and same metal. And also, the lanthanide is emissive, and as I said before, it exhibits a very unique photophysical property. So such as long lifetime and also large stop shift. And using this kind of emission lanthanide ion is very useful for preparing for fluorescent chemosensor. And also, this kind of cage exhibits very high selectivity towards the analyte because of whole gas interaction. If you have a very, very large analyte, then probably this one cannot go inside the cage. And the size of the inner cavity can be easily changed by fine-tuning the ligand structure. This one most of the time it applies, but for example, in the previous example that I mentioned, I think this one is not applied for it. But actually, there are many research reporting that a slightly increase in this linker size can also form the same product, and the cavity can be simply changed by increasing the number of phenyl ring on the linker. Okay, so one of the example of using this lanthanide supramolecular compound as the sensing of explosive and hazardous molecule. So one of the target explosive molecule is the nitroaromatic compounds. So this kind of nitroaromatic compounds are very common, and because their synthesis is very easy and inexpensive, and also this one is can be transported easily. So the current analytical techniques for detecting this kind of nitroaromatic compound includes ion mobility spectroscopy and also GC, gas chromatography. So on the right-hand side shows some of the example of nitroaromatics such as TNT and also petric acid. And here shows one of the example of using lanthanide supramolecular complex for detecting nitroaromatics. So in 2011, some scientists reported the use of this kind of C2 symmetric ligand. So it incorporates using EU3 plus ion to form two different supramolecular complex. Okay, so you see the same ligand, the same metal, but it forms two different supramolecular products. So this product was characterized by NMR and also ESIHR-MS to confirm the formation of this compound and also the chemical formula. But the tetrahedron topology can be only characterized by X-ray crystal structure. So in this research project, they succeed to confirm the structure because they got the X-ray crystal. And then after confirming the structure of this EU cage, and then they try to do some of the sensing for the nitroaromatic compound. So they try to put 5 different explosive nitroaromatic on the case, mixing it with the cage. And then they find that there is a selective luminescent quenching for this petric acid at the ppb level. So what they claim is probably the electron deficient nitroaromatic will form a charge transfer complex with the pi electron rich fluorophobe, which quench the overall luminescence. So on the left-hand side, you see the petric acid exhibit around quenching efficiency of 80%, while for the others, they just got 20% quenching efficiency. And for the right, on the right-hand side, it shows the emission spectrum with upon the addition of petric acid, you can see the emission intensity drop. So apart from nitroaromatics, scientists also utilize the cerium cage for sensing some of the other explosives, but not just nitroaromatic. So in the ligand design, this one is a tribotyl phase directed ligand. So they incorporate a DHPA group on the ligand, and upon the cell assembly process, it forms a M4L4 tetrahedron. And this tetrahedron is confirmed by the X-ray crystal analysis, elemental analysis, and also the MS. And on the right-hand side, it shows the MS peak corresponding to the cage, and also the encapsulation of the explosive called RDX. So this peak is very important because it's confirmed the encapsulation between the cage and the RDX is in the ratio of 1:1. So they further studied the sensing property of this explosive. So the encapsulation of RDX is, although it's already confirmed by HRMS, but they want to know whether the emission intensity is affected by this encapsulation. So as you can see on the left-hand side, the emission initially is off, but upon the addition of the RDX, it becomes a turn-on sensor. And on the right-hand side shows the change in the fluorescent spectrum addition of RDX, and then the radiative emission intensity increase. And here also shows the high selectivity of this kind of case, because they try to use, for example, TNT, DNT, and the other explosive, but only RDX shows a very high selectivity towards this case. So the emission enhancement is almost 7.5 times, which is higher than the others explosive. So apart from sensing explosive, this kind of lanthanide supramolecular case can be also used to sensing for the volatile compounds. So this volatile compound is very important in, for example, food industry and also environmental control. So this time scientists also use the same idea, using a phase-directed approach for constructing a tetrahedron. And bear in mind that this chelating group is different now. This one will be beta diketonomate. So this triportal case is, the structure is confirmed by the ESIMS and also by the X-ray crystallography. So here shows the X-ray crystal structure, confirming that this case is a tetrahedron. So they try to use this tetrahedron for sensing some of the volatile amine compound. So the sensing of this volatile amine exhibit a turn-on sensing, which can be attributed to the intra-ligand charge transfer in the ligand. So theoretically, this compound is not emissive because of this intra-ligand charge transfer from the 4,4 to the electron withdrawing beta diketonomate. But upon the addition of some of the volatile amine, there is a nucleophilic attack of the amine to the carbonyl group, which means here, and it will weaken the electron withdrawing capacity of the beta diketonomate. So on the left-hand side shows the enhancement of the emission spectrum upon the addition of the profile amine, and on the right-hand side shows the intensity change upon addition of different volatile compound. So you can see the oxygen containing volatile compound do not have any effect towards the fluorescent emission, and which shows that this case is highly sensitive to detect the amine, the nitrogen containing volatile compound rather than the oxygen containing volatile compound. And also this kind of self-assembly supramolecule is also can be also used in a biological application. For example, the sensing of carcinogen with the use of EU morph. So what's meant by morph? Actually, morph is also one of the self-assembly supramolecule, and morph stands for metal organic framework. So the preparation method is the same. They just mix the metal with the organic ligand together and then reflux it. But the difference is different from cage or helix because this one is a 3D network. That means the molecular weight is even larger than cage and helix, and the solubility is very poor, and that's why this kind of case is very difficult to characterize. So scientists use this kind of EU metal organic framework for sensing 1-hydroxypyrene, 1-HP, which is a biomarker of carcinogen. So this time they use this benzyl tetracarboxylic acid as the ligand, and to form a 3D morph network with EU. And this morph is characterized by powder XRD and also ICP-MS. And then they try to use this morph for sensing the 1-HP. So the presence of 1-HP caused the luminescent quenching of this EU morph. So here shows the luminescent spectrum of the compound. So the red one is the original morph. It is highly emissive, but upon the addition of 1-HP, the luminescence dropped significantly. And this can be attributed to the quenching by 1-HP. So they try to investigate the mechanism by doing DFT calculation, and they confirm that the quenching of this EU morph is not by PET, it's by FRET. That means the energy here will transfer to the 1 HP full FRET and quenching the energy transfer from the ligand triplet state to the EU excited state. Okay, finally, I would like to talk about one of the challenge when we are developing lanthanide supramolecular complex. Okay, so one of the major challenge is the stability of this kind of lanthanide supramolecular compound, because this kind of compound is not stable in water. And as you may know, the atom size is very big and it can accommodate a lot of ligand. So one of the ligand can be water. So most of the time when we synthesize a lanthanide supramolecular, is not stable in water because water will compete with the ligand, with the ligand, and then it will coordinate with the lanthanide, and then the whole cage will be dissociated. So there are not much lanthanide, water-soluble lanthanide self-assembly supramolecule. I mean, water-soluble lanthanide complex, there is a lot of example. But for self-assembly supramolecule that is water-soluble, there are not much example. So here shows a timeline, and I would like to compare the development with transition metal self-assembly supramolecule. So in 1995, Professor Fujita reported the first water-soluble transition metal self-assembly supramolecular case. And during this around 20 to 30 years, I guess, there are lots of examples concerning about this kind of transition metal compound, including the application of this case and also the theoretical study about the stability or the kinetics. Okay, so you can see in 2013, people even use this case for drug delivery, for self-imaging, and also for DNA sensing. So you may ask, how about lanthanide? Okay, so for lanthanide self-assembly supramolecule, the first case is reported in 2008, and this one is not water soluble. This one, when we add water into this cage, and then the cage will dissociate. And the first water-soluble cage is reported 2 years ago in 2020. That means there is a major challenge for developing this kind of cage. I think it's not easy to prepare a cage that is water-soluble. So here is the challenge for preparing lanthanide supramolecule. Here shows the comparison between 4F elements and 3D elements. So the most difficulty is the coordination number of lanthanide. So you can see for 3D transition metal, they are usually 6, and the bonding is covalent, so they have strong directional. And for lanthanide, the coordination number range from 3 to 12, and it's very difficult to control the formation of desired supramolecular compound. So the nature of bonding is ionic with few covalent. Previously, people think that the bonding of lanthanide is pure ionic, but recent research shows that there is a little bit mixing of orbital. That means they are still covalent. But overall speaking, the crystal field effect is very weak for lanthanide. This one is the first water-soluble case that I previously mentioned, and you can see they did quite a lot of hard work with the ligand design. So this ligand is completely different from the one that I showed you, and you can see they modify the coordination group. So they got an NH here, so they need to use a base to deprotonate this NH to become a negative charge. That means every lanthanide will coordinate with 3 neutral N and 6 N anion. And they also try to improve the stability and also the biocompatibility by adding the PEG on the ligand. So that means this is a very new idea and also a breakthrough in this research field. And okay, so thank you for your listening, and that's the end of this seminar. And I hope all of you think this seminar is interesting and useful. Thank you very much.
Okay, so thanks Ivan a lot for his interesting talk. So maybe for students, so any questions? So don't worry, okay, so our students, they are quite shy, okay. So maybe let me start first. So Ivan, so apart from using the X-ray crystallography, using the high resolution mass spec, or even using the ICP-MS, so what kinds of other analytical technique that you would apply to characterize the cage or characterize the things that you have?
I think apart from ICP, MS, and also X-ray, I think I will apply NMR, and I also try to use elemental analysis. But the beauty of this supramolecular is that actually we don't have to do any purification. That means if we do elemental analysis, then that means the result is not that useful. I would say it's not that conclusive. And I always describe the structure as tetrahedron. I always say it's a cage, a cube, and helix. And actually, this kind of structure can be only determined by X-ray. All the MS or NMR is not a direct method to determine it. Yes, but I think elemental analysis, that means CHN, is a quite good analytical technique for characterizing this compound.
Yeah, thank you. So I believe those kinds of supermolecule, they are quite highly sensitive and quite selective. So how about whether they would be quite portable so that you can do any on-site analysis?
On-site analysis, I think it will be possible in the future, because I think most of the compound that now reported is only soluble in organic solvent, such as acetonitrile and methanol. And I think this kind of organic solvent is not good for the environment. And I think if you are talking about on-site analysis, then I think we have to it's better to use water-soluble complex than some DCM or methanol or acetonitrile.
Yeah. So basically right now, the water-soluble supermolecule has been reported somehow 2 years ago. Yes. So do you think that the lanthanide supermolecule will be somehow overriding as a dominant supermolecule over the transition ones in the future?
I think in the future, yes. The reason is because they are unique photophysical property. I think this attracts a lot of scientists. But for the transition method, the crystal field and ligand field effect quite affect a lot about the energy level, which hinder the theoretical the photophysical use of this transition metal complex. But I think after the first the reported water-soluble lanthanide complex, I think there will be more use in the future.
Yeah, I guess for those kinds of lanthanide supermolecule, they are a kind of chemosensor. So how about what is your view on the comparison with the biosensor? Because right now, recently, everyone know that, let's say for the COVID, we have the RAT. So those kinds of things, they are biosensor using bioreceptor. So any comparison, let's say which one is better or which one will be somehow be more capable, okay, for further development?
Honestly, I'm not a expert in working on biosensor, but as what I know, some scientists already incorporate the lanthanide ions in some of the polymer. And this kind of polymer, most of them are biodegradable. And what I know is they utilize this lanthanide ion to incorporate in either polymer or some of the protein. And I think this may be a new direction for further developing biosensors.
Yeah, so I guess in the chat room, one student asked about the biosensor as well. So I guess I asked a similar question. So maybe Ivan, may you take a look on the question to see any supplement that you can make?
Yeah, I think that's what I told previously. I think this is a good question about the use of lanthanide in biosensor. And lanthanide is very useful, and there are lots of water-soluble lanthanide complex, lanthanide polymer, and some of the protein also even incorporate with lanthanide. But for the self-assembly supermolecule, I think there is still a long way to develop such self-assembly supermolecule for biosensor. But if you are talking about just advantage of lanthanide to apply this kind of lanthanide into biosensor, yes, there is a lot of example. And one of the example that I didn't show here is we call it cyclane. It's cyclane compound. The cyclane compound, I guess, let me see whether I can show some of the example. So, okay, sorry, and just a moment. Okay, let me open one paper. Okay. Okay, and then I share. Okay, everyone can see this paper, right? And yeah, actually, the self-assembly supermolecule, there are lots much example for biosensor. But if you are talking about, not this one, sorry. So sorry. And yes, this one. Okay. Yes, this one. Okay, so there are not much example for self-assembly supermolecule on biosensor, but you can see people utilize this kind of structure. Okay, so they also utilize lanthanide ion, for example, EU for sensing, and you can see the structure is different from the one that I report, that I use in this seminar, because this one is not considered as self-assembly. And you can see the ligand are well designed. You can see there are 4 N atoms, and then you can see a central cavity here, and then the lanthanide can incorporate inside the cavity. And then this kind of compound is very stable, and this water soluble. And most of the people use it for many different sensors, for example, MRI, contrasting agent. And in this paper, they also utilizing for the probes for biomolecule sensing. And some of them used to sense for ATP, and some people use it for sensing amino acid. Okay, so there are lots of different examples for lanthanide-based biosensor, but for lanthanide supermolecular sensor, there are not much example.
Okay, so I hope the question from the student has been solved. And then any further question from the student? So there's one more.
Okay. How do you design? Okay, so I want to answer the first question. You asked about the advantage. Actually, the advantage is about the unique photophysical property. That means if I use EU, and then it will give a very intense, sharp, red emission. Okay, that means the slide that I talk about photophysical property is already the advantages. Yeah, and how do you design ligand to bind specific target molecule? Is there some computer program? Oh, you are so smart. Yes, yes. I always said the design of ligand is very important for making for sensing some target analytes. But in reality, if we are really working in the lab, then I think there's not much method for designing a ligand that bind to specific target molecule. The only way is the computer program. I know some people in US or UK, they try to input the ligand design on the computer, and then they try to calculate the result. They can even calculate the result, that the supramolecular formation. That means they can know the design ligand can form either a cage or a cube or a helicase. So if you're talking about design the ligand for binding specific target, that means they have to first calculate the cage, the result of a cage, and then they can calculate the inner cavity, the size of the inner cavity by using the computer program. And once everything is okay, they accept, and then they will try to do the synthesis. But in most other countries, I think there are not much access to the computer program. And what we did is using some quite stupid method. We try to make the ligand, and then we try to do a compensation, and then we guess what we have. But in other countries, if they can access to some computers, they can calculate the result before doing experiment. I wonder if it's possible. Okay, so I wonder if it is possible to form stable Lanthanide supermolecule other than cube for cyclane. For cyclane, yes, I think cyclane is more stable. Do you mean cyclane is more stable than cube? I think yes, it is. Cyclane is more than cube. I think the stability is based on the ligand design. That means the coordination power between the ligand and the lanthanide. And for cyclane, yes, it is more stable compared with cube. But cyclane, some people think that cyclane is not cell assembly because everything is already there. You got a very stable, highly preferred binding site for lanthanide. And if you throw in the ligand and then you throw in the metal, and then you already know the result is 1-to-1 ratio. But for cell assembly, that means we don't know the result. Everything is governed by the hydrogen bonding or some non-covalent interaction. And that's why, yes, you're right, cyclane is more stable than cube.
So any further question from the student? Actually, for student, what you can see, so with the seminar today, actually it is a topic for a whole chemistry. So actually, if you look at those kind of ligand, maybe that will be related to the organic chemistry. If you're looking at the lanthanide, actually we bind together, that will become inorganic. Then you need to do some computation chemistry, that is the physical chem. And then you need to do some characterization, you need to do some measurement, that is analytical chemistry. So if you would like to apply those kinds of stuff into the biological application, okay, let's say some MRI or let's say some imaging, then that will become biochemistry. So actually, we will not say, okay, while we are now just studying analytical chemistry, then we are independent, we are isolated alone. Actually, we could be somehow engaged, okay, into a whole chemistry study. So actually, I hope, okay, so everyone today has been learned a lot from Ivan, okay, so really fruitful and also informative and very interesting, okay, for his sharing. So maybe at last, okay, so please join me to thanks Ivan again, okay, so thanks a lot.
Okay, you're welcome.
Okay, so maybe that is the end of the seminar. So for students, please be remember to submit the seminar report, okay, so by the due date. So otherwise, you cannot be graduate on time. Okay, so if there's no further suggestions or any else, and then just the end of today's seminar. Okay, so thanks a lot again, Ivan.
Okay, thank you. You're welcome.
Okay, so bye-bye, everyone.
Bye-bye.